In this video, we will be looking at a couple of APL primitives. We will be looking at how to carry arguments to a function with the bind operator, and then we will cover a bit of a synthetical amenity that APL provides. So if you are familiar with Iota and tally and with the bind operator and with modified assignments and with unpacking assignments or assignments where you unpack the values that you get, feel free to skip this video. Otherwise, let me get started with Iota, and I have no idea why I didn't talk about this earlier. This is one of the most useful primitives for me that I just keep typing a bunch of integers in a row to use as examples, and that's exactly what Iota does. So if you type, by the way, Iota is in APL I, as in Iota. If you type Iota 10, you'll get 10 positive integers or 10 non-negative integers depending on a setting you have. So if you look at the bottom right corner of my interpreter, you can see there, it says there's a square and then IO 0. IO stands for index origin in this particular case, and if you type APL L, you get this square which is called the quad. So APL L and then IO, it will tell you the value of your setting, and you can assign to it to change it, and the values that you can use are 0 and 1. And by default, IO is 1, so when you did Iota 10, you probably got the numbers, the integers from 1 to 10. I prefer to use zero-based indices, and so I set IO to 0. I don't think it will be important in the code we will be writing, so if it does become important, I will let you know. Otherwise, I would just recommend going with IO 0 because that's the more common approach in all other programming languages, and it will just make it easier for you if you get used to always having the same standard when dealing with indices. So that's Iota when the right argument is a single number. Go ahead and explore Iota a bit more if you want. Then we can use tally to find the length of a vector. And tally is typed with APL shift something. So this something is the key that is 2 keys to the right of the L. So in my keyboard, it's the quote key, and it's next to the enter key. So if this was too confusing for you, check the language bar at the top, and it will tell you what keyboard shortcut you need to press. And tally does exactly that. It tallies up a vector and tells you how many elements are in that vector. So if my vector has the numbers 2, 3, and 1, then the tally of v is 3. And, well, tally can also be used with matrices and arbitrary arrays, but we will be using it just to find the length of a vector. And then comes argument carrying. So carrying is when you have a function that takes 2 or more arguments, and you want to pre-assign some of the arguments so that you have a more specialized function. And what I mean by this is, for example, the power function can take any number to the power of any other number. But if you were to specify that the right argument is always 0.5, so if you want to specify that the right argument is always 0.5, then all of a sudden this, seen as a unit, is the square root function. And the way you do this is by using the bind operator, which is the same as beside, so the jot operator. APLJ is what you press to type this. So I can go right ahead and press enter. It just gives me a representation of the function. But the point is, I'm thinking how to show you this. Yeah, so let me enclose this in parentheses just to make sure. and to force the interpreter to see this as a unit, if I type in 25, I'm getting the square root of 5. And the reason why I used parentheses was that if I were to type in this, what APL sees is, well, here's two numbers, and let's give them as arguments, as right arguments to the power function. So this is called stranding in APL, and it's the mechanism that takes consecutive numbers and consecutive arrays and forms a larger array out of them. And I used the parentheses here to break the stranding so that this is seen as a function and then applied to 25. So keep that in mind. Sometimes this will bite you when you're not expecting. And so this is argument currying. Another example would be, let's say I'm going to define a function that's the nth root of the argument, and let's say, okay, we're taking the right argument to the root of the left argument. And here the division symbol, when used monadically, gives you the inverse. So divide 2 gives you 1/2, and divide 3 gives you 1/3, etc. And the point of having defined the function in this order is that now I can type in, say, 2 root 25 can be read as the square root of 25. And this gives me 5. And so if I were to create the square root, I could obviously do 2 roots omega, and then square root of 25 gives me 5, but I can also say the square root is the root function with the 2 curries, and then if I press enter, I can use the square root just as before. So that's argument currying. Now we're going to go over a couple of special things in assignments. So the first thing is, when you know the length of a result you're going to get, as in, for example, you have a function that returns a pair of things. Let me pair. So this function will do nothing, it will just return the numbers 10 and 20. So I have this function, and I know that whenever I call it with whatever arguments, I'm going to get a pair. And I know that the left element of the pair and the right element of the pair have specific meanings, and I want to assign them both to specific names to use them separately. And I can do that by writing opening parentheses and then left, right, and then closing parentheses, and then assigning the result of the function. And this unpacks the result of the function. And left takes the value 10, and right takes the value 20. Of course, this works for more than integers, and the pairs themselves could be more complex things. For example, let's make this a vector, and then let's make the second pair a matrix, because why not? Here notice that I'm using the index to populate the matrix. And now I can do the same thing again. I can unpack the results. So right became the matrix. So this is unpacking. And then I can also do modified assignment, which is something that's very useful. If you've ever programmed in any other language, you've probably seen this. Either on the form of, for example, I++ to increment a variable, or if you're coming from Python, you might have seen something like this, or even this. And in APL it works exactly the same way. So let me define some n, and now I can increment n by writing n gets n plus 1, right? And now n is 11. And this happens a lot. I could say that n will be n squared. I could say that n would be n minus 3. And this is a recurrent pattern in which I update a variable with a function and then some other value. And so this becomes n, and then the function you want to use, and then the second value. So this is the value of n. To increment n, you say plus gets 1. And now n is 119. To square n, you could say n power gets 2. And now n is this. You could even say n square root gets... Okay, to be honest, I'm not entirely sure this will work. Yeah, this does not work because square root is already a monadic function, so I need the function here to take 2 values, but using root, what will happen here? Let's see. Okay, so it does work because the pattern is when a variable n f gets a value, this usually gets unfolded to n gets nfv, if I'm not mistaken. And so, in this case above, supposedly what happened was n got n root 2. So what this means is that n, well, now I did it twice. Yeah, exactly. So n was set to the square root of 14,161. So if I just wanted the square root, so that this 2 represents the square and not the base, I could have used, let's set n to that again, 161. I could use the switch operator. So now I'm switching the order of the arguments. So I'm doing this, and I'm getting the square root of 14,161. And what this reads as is, let me comment so I don't execute it again. This is, so n root switch gets 2 is the same as n gets n root switch 2, and that is the same as n gets 2 root n. Yeah, that's it. Okay, so that's what's going on. And then finally, a convention that is useful is that when you're unpacking, and I completely forgot to mention this, sometimes you only care about some of the values. So for example, if I know I can safely ignore the left argument because I don't care, the left result, sorry, one would usually type this. And this is not a special syntax, it's just a convention that is used by people to say, okay, I know something's in here, but I don't care that much about the value. And I just care about the right value. And so you will see that often. Okay, so now we've gone through everything we needed. In the next video, the next couple of videos, we just have to go over a very powerful, pun intended, operator in APL, and you'll see what I mean in the next video. And then we will be finally implementing the forward pass of our neural network.